Hello, everyone. We're going to talk about section 9.5 on the kinetic molecular theory. The learning objectives here state the postulates of the kinetic molecular theory. Use this theory's postulates to explain the gas laws. So, first of all, the word postulate is just saying this is why, an explanation of why. You don't have to get into too much detail on that word itself. But the idea of the kinetic molecular theory is an explanation for why all of the simple gas laws as well as the ideal gas law work most of the time. And I mentioned I'd come back to this later. We're not going to talk about non-ideal gas behavior in detail, but as far as the ideal gas law goes, and we'll see as we go through this what that means in terms of when I say what that means, what the word ideal means in terms of kinetic molecular theory. But we'll get a sense of that here. But it's basically always true in terms of gases you would encounter in your life. There are gases that don't obey kinetic molecular theory, but they're very dangerous, so we try to stay away from them. But the air you breathe, anything else, any other kind of experiment you do, we can assume that the ideal gas law is a very good way of explaining or describing what goes on. In terms of explaining what goes on, that's when we turn to the kinetic molecular theory. So let's go ahead and read these ideas in the theory to kind of understand what we're saying is going on. So the first one, gases are composed of molecules that are in continuous motion, traveling in straight lines and changing direction only when they collide with other molecules or with the walls of a container. So the way this is often described is if you think of a pool table that may be three-dimensional instead of two-dimensional, that's kind of explaining it a little bit. So you have all of these things bouncing around the table, and they move in straight lines, and when they hit the side, they bounce off. They might collide with each other. This is basically what we think is happening to gas molecules. And if this is true, it actually explains the behavior of we observe with the ideal gas law. The second one, the molecules composing the gas are negligibly small compared to the distance between them. So this makes it a little bit different than that analogy of a pool table. So imagine that the pool table is, I don't know, the size of a baseball stadium, but the pool balls are still the same size, and they're still kind of bouncing around. So if you think of that, and there's the same number of them, then you're often going to be colliding with the container itself more so than with the other balls. So that one's important. Number 3, the pressure exerted by a gas in a container results from collisions between the gas molecules and the container walls. So when we talk about pressure, those collisions with the container are where that comes from. So that measurable property of pressure in our model, our kinetic molecular theory, that's where that's coming in. Number 4, gas molecules exert no attractive or repulsive forces on each other or the container walls. Therefore, their collisions are elastic, do not involve a loss of energy. So the idea here is when you think of the analogy of the pool table, you kind of watch it and eventually it stops, right? Eventually everything comes to a stop. What we're saying here is that that's not what happens with gases. Somehow they continue to move around and no energy is used up in that process. So with the pool table analogy, what we know is that kind of the rolling process, eventually the friction kind of slows it down. So we're saying there's really, when we say it's elastic, we're saying there's no friction. There's no amount of friction that stops these movements from occurring. And that's partly related to this idea of attractive or repulsive forces. The repulsive forces doesn't mean they don't bounce off of the walls. What it means is that there's not an extra kind of the balls don't kind of push each other away before they get close enough. Likewise, they don't stick together. And then number 5, the average kinetic energy of the gas molecules is proportional to the Kelvin temperature of the gas. So this one is the only one I would say that is not really intuitive. So we're just going to kind of accept this. And the idea is when I say the kinetic energy, think about how fast they're moving. So the faster they're moving, the higher their temperature. That's essentially what that is saying. So high temperature objects, when I say objects, I'm here talking about gas molecules are moving faster as they have a higher temperature. So just kind of accept that that one is true, and then we'll see how that makes the gas laws work. So we'll look at just this first part of the explanation. We're not going to explain all of the other things. A lot of those things we've actually skipped over already. So let's look at the first one. So if you're increasing the temperature, what that means in terms of kinetic molecular theory is that those gas molecules are moving more quickly. They're moving faster. So if everything else is constant, so the size of the container is constant, the number of those gas molecules are constant. If they're moving faster, they're going to have a higher impact when they collide with the container. So you're going to have a higher pressure. So hopefully that's pretty intuitive why that would make sense. For the next one, we're saying that they're not colliding more quickly. The container will adapt to them so that the pressure remains constant. So if they're moving more quickly and we want the same pressure, what's going to happen is that you have to have a bigger space. So they're moving more quickly, the space gets bigger, you end up with the same pressure. And then the next one. So if you change the size of the container, that wording here is a little bit tricky on this one, so it looks like they need to edit that. If you, let's say you make the container smaller, you're going to have more collisions if things are moving as quickly. So the pressure goes up. So container gets smaller, pressure goes up. Likewise, you do the reverse and you see the reverse thing happening. And then for this next one, we're looking at pressure and temperature. When pressure and temperature are constant, we're looking at the size of the container and the number of particles. So if you get more particles and you have them moving as quickly, you have as many collisions, then the container itself will have to get bigger. We're not going to talk about the Dalton's law one here, so we're just looking at those simple gas laws. So hopefully you can see that relationship between the kinetic theory and each of those gas laws. That is something that you would want to be able to talk about clearly. The rest of this section we're going to go ahead and skip through. There's some pictures here that can kind of show some examples. You can look at that if that is helpful to you. You don't have to know this relationship between speed and kinetic energy. There's some equations here. We're not going to worry about those equations. There are some graphs. We're not going to worry about those graphs. There are some things we skipped over. We're not going to worry about that. So that is essentially the end of Module 9.